Good evening, everyone. We'll wait for some time, then we'll start the session. Let the people enjoy. Okay, we'll start. Uh, we'll start the session today. And my name is MD Asad, and I'm PMRF scholar in the Department of Mechanical Engineering at Inner Tiruchirappalli. and I'm going to take the session as a PMRF TA as part of the PMRF engaging the session for the live courses that NPTEL that took. And so this session is for machine learning for engineering and science application, and we are on the week 11 of that content. So in the earlier week that we have seen around like how that is going that machine learning application for different field like engineering and science field that we see around and all. So as we can see that we have went through the structured way from the first week to the week. Now we are in the week 11, and if we see around, so we started with the very basic like what is the introduction to machine learning, and then we went to the linear algebra. In the introduction to machine learning that we have seen, we have started to introduce start started to introduce machine learning, and we all know that machine learning is something called we'll try to predict or classify based upon the data what we have instead of what we can like in the mathematical or in the traditional method we have to find out the solution. Like let's say where the data is there, we'll apply some concept, we'll get some solutions. But here we have the input, we have the output also. Now we are just giving the training to the model, and then they try to get into the what is the our output was there, and what is the pattern actually that what we have. So as we know, as we all know that it's machine learning is it's extension of the mathematics itself. So like to get the better grip of the machine learning, we should have some fundamentals or the background, like background theory, background for machine learning should be there. I'll just say like some brief, and then we'll start with the 11th week, and then I'll like what we are seeing here. We are trying to introduce the machine learning, and we'll go with like what is the like prerequisite of that machine learning actually. So first one is that actually is a linear algebra. Linear algebra is something like as we all know that like that classification of the image can be done, even that the parameter can be done. So that computers or the machine is not going to take as a in that the human as a input like in that, so that as a human being we can see around and we can visualize things and then we can see around. Okay, so I'm just giving the brief intro before jumping into the like the exact content for that our to like this week. And linear algebra is that why do we need of that's the linear algebra? That's what we're talking about. And as we can see that as a human being that we can see around, and then we can tell okay this is the things like it's a image of this image and that image we can say, and we can differentiate without any training and all. Even though like we have to get through in the starting, and then once we get to know that we can classify, we can recognize, we can do the pattern recognitions and all that we can see. But for a machines that they need the input in a number, and number is also in the binary number, either 0 or 1, and so they have fixed number itself is there. So that so whatever the input what we have, let's say I have the image, so that image can be of black and white image, so that we can convert into the RGB form, or we can give the their intensity like that RGB value, and then we can give the input like in convert into the tensor or the matrices and all. So that's what the whole agenda for the linear, that's the linear algebra. So in that we are discussing about the like that the matrices, then uh, that tensor, so that it will be easy to give the input to the machines. Like machines can't take everything or anything as an input. They need in terms of the machines itself, like in terms of the number itself. So that's what the linear algebra will do. And even linear algebra will like they will calculate another transformations and all to get them get the matrices to be done and all. Then the second say the so that the second parameter, that second prerequisite for the machine learning actually. So second prerequisite is that actually we should have the knowledge of the probability. So that the many machine learning model that actually works on the probability, like what is the threshold value, what is the actual percentage of the chances that is going to come for the true classification or true regressions and all. So we should have the probability, or sometime we have to talk about the conditional probability also, joint like a probability also, and even we have one that model is that the Bayesian classification is there, and like a Bayesian regression is there, and the same is actually in what we have is the generative adversarial, that the network also its work based upon the deterministic model or the it's a probabilistic model and all. So we should have the brief idea of the probability also. So once you are get into the probability, like if you are into the data science and all, so then you can go through that statistic also. Statistic also, let's say I'm like for a particular model, I have to get the features. Let's say for a model that so that need to be done. Let's say I have to do the classification for the signals. Signals will be having different like properties are there. Time domain, frequency domain, and time frequency domain. Then entropy parameters and all are there. So what can be done? Like okay, for that particular or for any specific applications, is it that features have significant differences or not? If it is not there, so what will happen, it's going to bias them, because both are not having the any significant difference. Let's say I have two class, one class is fatigue class, second class is going to non-fatigue class. So if it is, I'm going to calculate the feature for the fatigue class or the fatigue feature for the that's the non-fatigue class. And if I have done the testing, by seeing the naked eye, we can see the number differences are there. But once we'll do the testing, t-test, ANOVA test, or maybe that Wilcox test and all that we'll do. We'll see. And then how many we have? Okay, so we have to see around like if the feature fatigue, if the both feature with both doesn't have any differences and also what, so there will be chances of the either overfitting or that underfitting. So that we have to do some testing, either the t-test, ANOVA or ANOVA to get the differentiation, and then sometimes we have to do the dimensionality reductions also, because if we'll give the any feature that doesn't have any, so that doesn't making any differences, so that will go into data will be the redundant, and then a computational power is going to be like more. So we have to what we have to do, we have to check whatever the feature that having significance difference between the two class or two groups or two groups and all. So that we have to do through the statistical testing. In the statistical also we have different types of tests are there. Uh, like ANOVA is there, F test is there, T test is there, and other tests that all that we have to deal around and all. So once we'll get to know that the probability and the statistics, and then we have to talk about the computation or optimization. Why do we need the optimization? As we all know that when we have to do the classification or we are doing the regression, so there be as like some sort of actual versus predicted or classified will be always some difference will be there. So that error should be minimized. For better model, what we do, we have to like that model should be optimized, or so that error should be less, and the performance their parameter should be high and also that comes under the optimization itself. Further, but we have that gradient tensors are there, and that other factors and all we have to calculate, and all Hessian matrices and all are there. So now we'll coming to the introduction to machine learning packages. So that we have seen this course actually fully dedicated for the MATLAB itself. Actually, in the MATLAB also, MATLAB also, we have statistic and machine learning toolbox will be there. So this is the one way that just feed the data. We have a select from drop down model. We'll select it and then we'll calculate the data set history, like data set participants and all. Then we can get into that directly. There's another way is that if you are good enough into the code, you just write the code and then feed into the model. You'll get the better results and all. So that's how the things. One more things will work it out. Similarly, the MATLAB we have the Pythons are there, and then others software packages will be there and all. So then this is the whole 3 weeks that we have started with the prerequisite of that machine learning course that we have to jump into that. So now we'll go with the starting or fundamentals of the regression, like it's called linear regression or the logistic regression. Linear regression is something that we have to do the forecasting, or maybe that price estimation of price rent, that the rent forecasting, or maybe that the rain for rain predictions and all that we have to do. Logistic, like in the linear, they're going to do like y is equal to mx plus c, but it convert into the sigmoid function. So it will go to the logistic regression. Just 1 minute. Hello, अभी क्लास चल रहा है. Okay, so it will convert into the logistic regression. Logistic regression is something that they're going to deal about like non-linearity and all. Non-linearity and all. And in that only we are having the bias variance trade-off. Like when the bias is more, so we'll be having that model will comes under the falling the category of the underfitting. If the variance will be more, so that model will go into the category of the what we say overfitting. So this is how the variance to bias trade-off will go. So this is the optimal value, and this is actually uh, bias having more. So this is underfitting zone. Then this is the variance will be the high. This is actually a overfitting zone. So we have to make the balance between the like underfitting and then overfitting both. So what is that regularization? Regularization is something that we have to prevent underfitting or overfitting. So there is a L1 regularization. It's called lasso. Then what we have the L2 is that like ridge regularization. So that's the thing. Then the variant of the gradient descent, like first one will be there. Then the Hessian is there. MLE is that the maximum likelihood function. Maximum likelihood function. And then MAP is actually maximum a posteriori. It's actually will go into the Bayesian regression. You know. So this is some terms that we have to deal about while dealing the models and all. So where we have to think about all these things and all. So then week fifth we have started with the like basic of neural network. It's a ANN and all. If there is a single hidden layer and all, that will come from that like ANN. And if that the number of that hidden layer is one, that the more than one, it will go into deep learning and all. So in that only that the multi that layer perceptron will be there, and it actually works on the based upon the like what that. So they're going to mimic the human, and that the nature of that human tendency of that neutron nano. So in that also, but we have two like methods are there. One method is actually like what we have is actually forward propagation. then the backward propagation is there. So forward propagation actually is the comparatively expensive and it's a simple one. And then backward propagation actually it's going to work on the chain rule, and it's easy and not easy. I can say it's going to less comparison expensive. So that's why the people will are like they are going to more aligned with the backward propagations and all. So if you see around what is that applications of the neural network and all, so that we can go to the application will be like a pattern regression biomedical field or imaging, CT scan and imaging will be image processing will be that will be there. So in that only what we have one model is there, it's called a CNN. CNN is actually CNN actually they need the input as the image. Let's say I have to do the image processing or image pattern recognition will be there. So either we can take the picture through the pixel. Just 1 minute. Okay, so what's their CNN operation like a scene architectures and a CNN actually they need the input as an image, like input as an image, and image either you can get to the pixel phone cameras and all, or either you can convert any of the signals to the image, or even that any text writing and all that you can convert into the image and then you can feed it to. So that image actually we can't directly feed into the like that the machine learning model or CNN model. So that what we have to do, we have to convert into the tensor. That can be go to the 28 by 28 or 32 by 32 or 64 by 64 tensor image that will go, and then we can feed into the CNN model. Then CNN architecture is what we have. It's that the block is there. Then another will be like flatten layer, and then again we have to like open it up and all. So then second one what we have there is the transfer learning. And then optimization function, that's the Adam functions and all will be there. So that we have seen in the in initial weeks and all. Transfer learning is something that what we have. It's the initial learning that was used for the preliminary studies, and then the same is that the results going to feed into the actual model. It's called transfer the learning. It's something. Let's say I'm going to learn squat, and then like let's say I have to do the sprinting. So what they will do, like what we will do, we'll do the training. Training will be it depends upon the jogging and all, then other like strength training and so on. So whatever we have learned it, now we transfer into the sprinting time. So that's what the things is. It's called the transfer learning and all. So where it's going to use it out, image processing, even CNN can be used for that regression also. That's the very and all. But the CNN in terms of regression, it's not given as good as results. So to deal with that, what we came across with the RNN. RNN is something like it's called recurrent neural network. Recurrent neural network is something like it's a continuous like that we can do. It's a time series domain or temporal or spatial domain data. We can play about that because the CNN actually they're going to do either it's a classify like a fatigue or like there's no fatigue happen or a spam. So there's no like a spam. So it's just a classification. It's a 2 point classification. Multiple classification we can do. There's no much issue with that. We can just add one more class or group and we can do it. But the thing is that to get for the temporal or a spatial value or a spatial pattern recognition, so we have to come up with the recurrent that's the neural network, and extension of that LSTM is actually it's called the LSTM. It's a long term, short term memory. So it's again it will deal with the like it's going to take the pre data or a pre like their training values also, and then they're going to store it like it's based upon the history. Like let's say I'm going to say I have run for the some 1 minute or 2 minute the sprinting I have done. So the thing is that how my muscles is actually react is going to it's not about the point to point how it's so LSTM will they will take the from the backward also, then from the forward also, then they're going to store it and then train it, and then we can get the better results and all. Then after week 9, we have seen the Bayesian regression, Bayesian or random forest, like it's the traditional classical techniques that we have seen around. I have seen a traditional account like like a binary decision tree, and maybe the base like it's like a naive Bayes classification or SVM. SVM is going to create a hyperplane. It's a 2D plane that going to create between the two class one two. So actually, this is mostly for that linear problems. Once we have to deal with the like something called that like we what we have the nonlinearity will comes into picture. So we have to introduce some kernels will be there. So they are going to deal with the nonlinearity and all. Then the binary tree that we will be having, we're going to create at the root leaves and all. Then we can create it. So random forest is something. It's a combination of the like that the multiple by like a decision tree. Like in the random like decision tree, it's a very basic method, and it's like mostly dealing based upon the what I can say gene index and then entropy itself. So that the random forest is going to deal like will be having multiple decision tree, and it based upon that like we're going to create the random forest. Like it will be 70, 60, 80, 100, or it depends upon that. So that's how the and Bayesian classification is actually it works based upon the what I can say is the probability. It's called like that we have is the new Bayes theorem. Then so this is the sum all of like a supervised machine learning. So then when we but we have the ensemble learning is there like XGBoost, AdaBoost and all. So what they will do, what we're going to do, we are going to take a decision tree. We're going to keep in either one group in that multiple trees are there, two groups. Second, that the multiple tree will be there. Third group will be taken. So accordingly, then we're going to take the based upon the majority. One, two, three, four groups are there. We'll take the based upon the majority, and we'll decide like that particular or that how the data is going to classify and all. So then what we have the unsupervised machine learning, it's called the K means and KNN, K nearest neighbor, that's called. So it's something like we don't have the data will be labeled. Data will be not labeled. It's going to based upon the distance how we're going to classify. We're going to create one plane, hyperplane, and then we can create the distance, and we have to minimize the like a distance. So in the unsupervised machine learning, we don't have the data will be labeled, but it will be going to taken based upon the that Euclidean distance and all, and we have to minimize the like distance and all. Then what we have is that KNN actually K nearest neighbor, and that expectation that maximization and all. The last class what we have seen is the advanced probability probability model and all. And like now today we are going to see with the like a generative adversarial and that network will see around. So before that what we'll see, we are going to see what is that that map and Bayesian regression. So map is actually it's a like it's the maximum a posterior like a posteriori estimation. In that like we have will be having some conditional probability will be there. We are having two terms, MLE and then MAP. MLE is actually maximum likelihood function. In that, we don't have much of information, but that we don't talk about the history. But if you see around in that map, we have to deal about the like the previous knowledge should be there. So it's a contain all the knowledge about the unknown quantity. Therefore, we can use the posterior distribution. And to find out the interval estimate of the x, we can obtain point estimate is to choose what x that maximize. Let's say this is how the things will go for that PMF, probability mass function, and this is for PDF. It's a probability density function. So so for the each point, so we have to know that all the values will be there for the all the unknown quantity and all, and then based upon the we can get the value of the probability for that whole structure or the system. So to find the map estimate, we are going to use the Bayes theorem. So what they will do? Probability of x and x given y. So what we will do, we have to calculate the this value y given x, f of x that already given, and f of y. So then we know all the value. It's a conditional value. This is going to be a it's a conditional probability and all. Uh, so if y does not depends upon the value of x, so then we can write the f of y of x, y given x into fx. So it means like it's an independent value. So independent value that simply we can't, this one is not going to, it's become the same term. So what we have to do, either we have to observe the y is equal to y so that we can find out the value of the x that maximizes this value. We have to maximize this value to get the maximum probability, because we have to know the all information about that. So this is the MAP actually is will be having all the information, and that all information you're going to use to find out the their that maximum probability, so that we can give that, so that model having the better information and all. So let's say one example is there. So what we have, it's a geometry function is there, and fx is equal to 2x if 0 to 1, otherwise 0. So it's a geometry function is there. So how we can calculate the MAP? So we can see around. So it's geometry functions. So p of x y of x, y by for a y given x, x is equal to 1 minus x by y minus 1. It's the geometry functions. We all know that for the geometry functions at all. So for the value of 3 for the given x, so x into 1 minus x square, x to the y is equal to actually how much we have. So it's a 3 minus 2. So it become 1 minus x 3 minus 1. So x into 1 minus x whole square. So now we need to find out the value for the 0 to 1. That maximum is 0 to 1. X into 1 minus x square into 2x. F of x, how much is there? We all know that f of here, we can see here, f of yx will become y given x into f of x. So we have calculated this value, and then f of x is actually 2x. Okay. So now x into 2x, so 2x square into 1 minus x square. So now to get the maximization or minimization, so we have to do dy by dx is equal to 0. Like it's a general term we have to do. So dy by dx, x square, 1 minus x square. So now if we apply the chain rule and equate to 0, we'll get x of map is equal to half. So it's a simple algebra and then all that we can do around, and then we can get the result for the x map and all. Now we'll come to the what is the posterior probability. In Bayesian statistic, actually, it's the probability is the revised or updated probability, like after getting the information from the previous. So this is actually a posterior, and this will be the prior probability. Okay. So the posterior probability is calculated by updating the prior probability using the Bayes theorem and all. So posterior probability is the probability of an event occurring after taking into the new information or evidence. It's something that we have to incorporate the prior probability, and it's going to calculate based upon the Bayes theorem. So which is going to relate with the conditional probability of the true event. So can we see one example like what we have? It's a, suppose a medical test for a rare disease has a false positive rate, false negative rate. Prevalence of the disease in the general population is actually it's going to 0.1 percentage. So it's again 0.001 it become. If the person test positive for the disease, what is the probability of that person actually has the disease? Like I say, next one. A person will be having a disease. B, positive test result. So given probability of B given A, it's a true positive rate. It's a 0.98. So probability of B, it's not like true negative rate. It's going to 1 minus of false positive rate. It's a 0.95. So now they are given P of A, prevalence of the disease they have given. So now using the Bayes theorem, like a probability of A when the given B already there. So probability of B by A into PA by PB. So PB like it's something we can use the probability of the positive test. PB is equal to PB probability of the B already A done plus into the probability A plus probability of A that A did not done and probability of that A does not happen. So 0.98, 0.2, 0.001, 0.05, so it will come this value. So now we can apply this to the Bayes theorem. So we'll get the this value. So that's how we'll get the 1.9 percent like a probability that person actually has the disease. So it means we are going to incorporate the previous results also. Okay. So what is the prior probability? As I told, this is going to be our posterior one. This is actually a previous. So this already given by initial assessment. So it's something probability defined as an initial assessment or likelihood of the event or outcome before any new data is going to consider. It's something like we'll tell what we know based on the previous knowledge or experience. So it's a that's something that already happened or by using the some initial assessment that we are seeing around. So now we'll tell the definitions between like what is the comparison between the MLE or map. So actually, MLE, what they'll do, so they're not going to consider the prior knowledge. It's going to work on the point and not having any prior knowledge. Just one minute. So that doesn't have any prior knowledge and all. MAP actually they're going to use the include the prior distributions, making it more stable when the data is going to scarce, like when we don't have much enough data and all. So that they're going to use, and we can get the MLA is a special case of the map when prior is going to uniform. MAP estimate prevent overfitting by incorporating the prior beliefs. Now that's how the difference between the MAP versus MLE we can say. So now we'll talk about the regression, Bayesian regression. Before that, why do we need like what is a linear regression? It's actually assumption that underlying data is normally distributed and that all relevant predictive variables have linear like it's going to linear like a linear like relationship. It's called y is equal to mx plus c. So with the outcome, but in the real world, this is not always possible. What will happen? It's always there will be some sort of like non-linearity will be there. So we have to go with the either with the Bayesian or we can go with the logistic regression or other regression model. So why the Bayesian can be like a better choice? Bayesian regression actually they're going to employ the prior belief like previous knowledge about the data to learn more about it, create more accurate predictions. It also makes the into account the data uncertainty, and they're going to take the previous knowledge so that it will give the better prediction and all. So this is actually for the ideal choice for the when the data is going to complex or ambiguous. Ambiguous like we don't have actual patterns or it's some random patterns are there and all. So Bayesian regression actually to estimate the parameter of a linear like the model, incorporating the both observed data and prior belief about the parameters. Unlike that the ordinary that the least square regression which provide the point estimate, Bayesian regression provides the probability distribution. It's something that we are going to have based on the probability, or and sometimes that we're going to use the offering a measure of the uncertainty in the production, like in the prediction. Okay. So, what is the base theorem actually? Base theorem is actually probability of A when the B already given. So that's how we can calculate and all. So probability of the A is the B, like posterior probability after observing the data A. It's a prior probability of B for the marginal probability of that observed data will be there. So Bayesian predictions, it's going to the map estimate is a still a point estimate. It's not going to with the continuous one, either random or continuous variable. Okay. So it provides a posterior distribution for error of estimate in W, prediction for the new value of input data, Y test for the given X test. Bayesian regression is all about to determine the predictive distribution. It's based upon the okay. So what is that likelihood function? Likelihood function represent the probability of the observed data given certain parameter value. Like it's something assuming that what we have probability of the observed data for a given certain parameter value. So it's assuming the normal error, the relation between the independent variable x and target y is going to be a like. So prior and percentage like distribution, it's going to be like it's going alpha represent the prior knowledge about the parameter before observing the data. Posterior will be x alpha beta. It's something that we have to give incorporate the all the parameter like we have to include the learning rate and all. So, what is the need of the Bayesian regression? Actually, it's going to handle the limited data set, incorporate the prior knowledge, making it effective when data is going to be scarce. Uncertainty estimation we can do. Even now, the people also are more of working in the uncertainty and all. So, as uncertainty is something that we are able to say if I'm going to give introduce some uncertainty. Let's say a person have run a model, so now they are able to say how accurate the results are there. But the thing is that whether if we introduce some uncertainty, whether it will give the better results or not. Like it's we are how much confident that we are having the results or not. Earlier we said okay, we run the model, we got the results, we have given this value, but we are not saying how confident the so that the models are there. So what we'll do, we are going to introduce some noise or some uncertainty, or we'll roll some data and all. So whether they are able to give same results or not, or either the same level of the results are there or not, so that we can calculate through the our like Bayesian regression, or even that the probabilistic models and all. So then what we have here, what we have we have the flexibilities are there, so they can deal with the complex relationship, and then like it's going to be a non linearities also we can deal. So means we can deal about the linear also, non-linear also, complex also, and it's all we can integrate that integrating with the prior knowledge or the history itself, like we are taking or we are learning from the previous history, and then we are going to implement into the our future models and all. So then the we can do with the same with the like it's with the model selections, and like enable the comparison of the different model using the posterior probability and all. So we can do the comparison, like let's say when we didn't consider. So what were the results? Some results came, some X value results came. Second, but once we introduce the probability, like what is the result came, X and Y. So now we can compare between the X and Y model. X model that doesn't consider the history, or they're not going to learn from the previous history. They will take at that particular point itself, and then then the Y model is there. Y model is going to take the data or input from the previous data history also, and then we can take at the point itself. So now we are able to compare between the like that model, so that which one is the best model, so that we can use for the like real time deployment for the variables and all that we can use it out and all. Then it will be robust to the outlier, reduce the influence of the extreme value, making it the more stable than the classical regression model. It's something here the error chances of the error will be the less, or even some values are going to be that the outlier. It will not affect much result as compared to the what the classical regression method that might be affecting the results. We are not sure. Once we'll run the model, we'll see whether it's affecting or not. But the thing is that there are chances it might influence, or that so that the outlier can influence more into the classical classical regression method is compared to the what we have, that the probabilistic like this models and all. So what is the formula for that? So Bayesian regression formula, if for the for the linear relationship, we'll be having y is equal to and all. Assumptions will be the so that the error terms will be always independent and identically distributed. It's a IID, identically, and the target variable y follows a normal distribution with the mean and variance. It's again same thing but we have. So what will be the conditional probability of that functions for PDF function? Probability of the y for a given when they are going to be having a normal distribution, so it's going to get as like it's a normal distribution. For the n observation, what we have to do, we have to get the probability for the n times. Then after we simplifies based upon the that all n value, then we have to get the logarithmic of the that likelihood functions, and then we have to maximize the error. Okay, so then so then we have to maximum a posteriority. We have to apply it here. What is the precision term? We define precision beta as the beta is equal to 1 by sigma square is the standard deviation. And substituting the likelihood to log functions, and then negative likelihood functions, then we have to go into maximum. So we have to do maximize. Okay. So minimizing the expression gives the maximum. Like this is the error terms. If we minimize, it will give the maximum. It will give the maximum posterior estimate, which is equivalent to the ridge regression. It's called L1 regression. L1, L, L2, L2. And L1 is actually a lasso. Lasso regression. So Bayesian regression provides a probabilistic framework for linear regression by incorporating the prior knowledge. Instead of estimating a single set of parameters, we obtain a distributions over a possible parameter which enhance the robustness in situation with the limited data or multi-collinearity and all. So Miss Bayesian are giving the better results as compared to the classical regression methods and all. So so if we talk about the feature like comparison between the so traditional assumptions will be the data is going to follow the a normal distributions, no prior information. Incorporate the prior distributions and uncertainty. Like data should be normal distributions should be there. Estimates will be point estimate of the parameter. Here, probability distributions over the parameter. It's something like it's point estimate, but here we can get the in the uh, probability distributions in the either it can be a PMF or it can be a PDF. Both can be there. Then what we have the flexibility limited assume the strict like it's going to be a linearity, high flexible, can incorporate the non-linearity and all. Data requirement, maybe a large data set for the reliable estimates, and but it can work with the small data sets also. And uncertainty handling, it not quantify the uncertainty, but it will give the better via posterior distributions and all. So when to use the Bayesian regression? It's when the sample size we have the limited sample size will be there. Okay, so then a strong prior knowledge, but we have the some domain expert is already available incorporating the prior enhanced model like reliability, handling the uncertainty also. If quantifying the uncertainty in the prediction is essential, like uncertainty quantification we should have to do because for a better good accurate results and all that we have to get the confidence label. Once we'll go with the any of the variables, we have to tell how confident the results are. Okay. So now just wait for 2 minutes. We'll come back. Okay, so now we are going to start with the generative model. It's a advanced machine learning technique. It comes falling under the category of semi-supervised semi-supervised machine learning and self-supervised machine learning. Okay, so if we talk about the supervised machine learning, that what will be having the data will be the label. Data will be linearly separable. Data will be there. Okay, so in that the data will be already labeled will be there. So then we can create the plane, and then for that what we have the model is the SVM, random forest, decision tree, or ANN also is there. Even we that can work on the unsupervised also. So aim is to learn the mapping from the X to Y. Like we have to have the input to output, we have to do the mapping, and then one feature, second feature with that will be there. Then second one, what we have the unsupervised machine learning. Further, what we have the classification, regression, object detection, semantic segmentation, image captioning also we can do out and all. So unsupervised machine learning is actually will not have the data that will be labeled. It will be a random data will be there, but will do like that will be having some sort of some pattern will be there, or some group that will be having the closer that features will be there, so that we have to take it into account, and then we have to make the cluster. It's a actually a cluster. It's a KNN or clustering. In clustering also we have the hierarchical clustering is there, agmentic clustering is there. So learn some hidden representation of the data. It's something we don't have the exact pattern, or we don't have the exact labeled one. What is the actually it is, but we have to learn from the hidden pattern. So there, so example is it's going to be clustering, or maybe that dimensionality reduction and the feature learning, and then density estimation will be the like what will be having the for this model, for the unsupervised machine learning model. So now the comes will be now so that we have deal about even we have deal about the deep learning also, and all we have seen that the neural networks and all. So now the things will be there. How can what is the generative model? What is the generative model? Let's say one feature is there, second feature is there. Now we have the we know the pattern, we know the things and all. Now we are going to regenerate by mapping the their distributions and then parameter model that addresses the density estimation of the data, a core problem in the unsupervised machine learning. Here we have to find out that like density estimation. Density estimation is actually generate new sample following the same probability distribution as that of training data set. Is something like what we have. We have the some data set is there. From that same data set, using the same like distributions, we have to generate the new data set so that we can get the like better understanding of the data and all. So a generative model is a machine learning model designed to create new data that is similar to of its training data. So it's something we have to create the reconstructions, we can say. If we talk about the signal, it's a reconstruction. So what is the generative model? Generative model is something that we have to make the reconstructions, or like to generate the data, whatever the earlier probability distributions is there, we are going to create a new data set. so that it will give the pattern, like it's going to generative artificial that learn the pattern and distribution of the training data and apply that understanding to generate the novel content in the response of the response to the new input data and all. So generative something like what we have, we don't know the pattern, we know the like their distributions. So we're going to generate the data, we'll get the their features will say latent space and all will say. So, where it can be used, let's say I have to get that input image and then, or maybe that converting from the black image to the color image, or maybe from this heat thermal image to the actual facade, from day to night, we can convert it. Even this input was there, we can convert into the color one. Like it's something like we have to regenerate the image, or even we have some ancestral parameters are there, and then so that the same can be like regenerate with better resolution. That's what the term, like it's going to application in the generative AI and all. So what can be the other images, image to video, educational also, like the virtual tutoring and all, assignment assistance or curriculum design. And even we can use for the architecture and constructions also, architecture design will be there. So let's say we have some Pinterest image is there, from that we can convert it into the actual architect with using AI. So this is how things will do. Like it's a generative AI, not the AI, it's a generative AI. So that can be done. Even some some architect will be there. They're going to deal with that. So that architect they'll be going to design from the scratch and then they'll give you the better one. Sometimes that what we have will be having the for better aesthetics. We'll take the some images. Let's say some people have some better connections or better some connections from the previous history and all. They'll say I have this picture into the mind, or I have this picture. So now I want to get the actual picture or architect of that design. So that can be done through the generative AI. Then even we can use for the business also. It's a sales and marketing, customer support, and then report and like a dashboard generation also we can do. Even the people are doing with the cyber security also. Then in that what will they will do, intrusion detection system, security awareness they will do, and then privacy protections, and then the risk protect risk reporting will be there. Then what we can use the metaverse. Metaverse is something like it's a personalized avatar. Like if you see the movie Avatar, so they have used the fully generative AI, and then virtual world building, real-time interactive storytelling. Like even we can see the agentic AI is also coming into the picture. Agentic AI. Whatever asking to the chat GPT, I'm asking to the DeepSeek and all. There's a agentic AI. I'm asking the any question, and then agent will take keen into that, and then they're going to do the deep search, and then they will come into the pictures and all. Then even we can use for the agriculture also, healthcare also, legal analysis also, and audio and speech. It's a text to speech generation. It can be done through the generative AI. Even the chatbot also, it's a generative AI. Let's say I'm going to search in the YouTube. So there is two options are there. One that we can type it out. Second one we can put the audio. Or like we're going to speak, and then based upon that they're going to search the results. They'll give it out. So even the content generation also, it's like a caption. Let's say I have the YouTube videos. We'll keep it out, and then we get the like there and now. So then the like even that can be done for the that the writing assistance also. Then generating the data for the training also. Let's say we have some data is not actually proper, or maybe not proper means like it's less data set of the number. So we can get the like to generate the medical image or specifically anatomy also. Even for the image to image translation for the medical imaging applications also, let's say in the CT and pathology also we can do out and all. So What is that actually? It's act of content generation. Content generation is not something that the people are that any influencers are doing. Here, it's something what we have the initial training data set. They're going to reconstruct or like regenerate the things, and is what separate generative AI model from the other types of the AI. So other AI model, it's not going to generate and all, but what the you will give the feed it will give the based upon their results, they will give it. Here whatever will feed it out, they're going to first reconstruct and then we are going to give the, they're going to mimic the actual picture of that, well, like that the human brain knows. So it's actually genetic models are advanced that the neural network that mimic the structure of the human brain and apply the complex machine learning algorithm to process the training data and manufacture the new data. It's like a generate the new output. So generative AI type of the AI that use sophisticated model to generate new content according to the input prompt. So it's actually computer program that employ data algorithm to facilitate the practice of the generative AI. Generative AI used case include the text summarization, text generation, and even with the image generations also from low pixel to high resolution or pixel, as well as the 3D modeling and audio creations also we can be done through the generative AI. So how it works actually, how it is going to work? Generative model is going to work by identifying the pattern and distribution. Distribution pattern is something like it's a density distribution. If you see around here how it was showing, it okay. So they are going to learn from their pattern and distribution in their training, rather than applying those findings to the generation of new data based upon the user input. It's something we are going to get. First, we are going to find out the like pattern, then we're going to generate. Let's say one I have. So this is the input. Then after first part will be it came like this. Third will be close will go. At after certain time it's going to perfect regenerate. There will be a like minimal that the loss of reconstruction will be there. No. Okay, so generative model are typically trained with the unsupervised machine learning. Unsupervised machine learning, it's something will be the clustering or dimensionality reduction. When they are fed a mass of unlabeled data sort through it by themselves, the model figure out the distributions of the data, which is how they cultivate the internal logic. Then they can create the. So it's actually that the mostly is going to work based upon the unsupervised machine learning only. We're going to feed it the one like sort of data. Will not tell which data and how it's going to work it out, and then they're going to figure out that what is the distribution of the data. Then they're going to give the create a new data. So there, the training during the training, the model applies a loss function to measure the gap between the real world outcome and then middle predictions. It's so the goal of the training is to minimize the loss of function. Loss function, bringing generated output the close to the output as possible. That I told, loss of reconstruction or regeneration, we can say. So in that case, like it should be as much as should be low possible. Then content generation is a probability poster like a process, and genetic model do not know the things in the same way that human do. So for that case, so genetic model, yeah, that going to use the complicated mathematical equation to predict the most likely output based on the rules it learned from the training and all. It's something like they're going to learn from the input data and then going to generate the that the most likely function. It can't be 100% like they so there will be zero loss will be there. So it's not possible also sometime. Okay. So they are going to attempt to generate the new data of a certain class. Let's say I gave one signal, it like this and all. So what they will do? They're going to create one like canal. Again, they'll learn from the previous. Again, they will come closer, very closer. Simply, it will go. So here, discriminative model separate items into the known groups. It's again with the case of bagging. Yeah. While clustering model figure out how to group item in a data set. How to like in clustering based upon the which value we will do the clustering. So predictive model makes estimation about the future occurrence and states based on the historical data. It's a based upon the historical data itself. So discriminative model are used in the supervised machine learning. It's a classification which label or categorize the data that are known. Many descriptive models are classification that attempt to identify relationship between the features and the assigned class label. So then they are going to label to a new data based on the conditional probability of those models. Hmm. So for example, we'll see a discriminative model trained to differentiate between the image of the fish and birds can guess whether image are more likely to be the fish or birds. Image recognition, a type of the classification in machine learning, is a common application for the discriminative model. While generative model and discriminative model have distinct features, differs. They often work together, such as generative adversarial network. That's how so that one model comes into the picture, generative adversarial network. So what we have like what are the types of the model we have? Clustering model. Clustering model they are going to use for the unsupervised machine learning task to group record within the dataset into the cluster. So they can identify similar item and also learn what separate those items from the another groups in the dataset. So okay, so means clustering they will do. So they're going to like create the cluster. Then after they will learn identify by themselves like identify similar item and learn what separates that what features they're going to separate from the one to the second group. Clustering model lack prior knowledge of the item in the dataset, including that knowledge of how many groups are there might be. A market researcher might be used clustering model to identify the buyer person with their target demographics. So then one more what we have a predictive model. It's a historical data to make the prediction about the future event using a it's a machine learning and statistical analysis. So they are going to often use the business leader make data driven decision like in first quarter how much sale happened, what is the profit, what is the loss happened. So actually for the text services, facial recognition, software, fraud detection. And generative model actually for the unlabeled data during the training, they reverse engineer. Reverse engineer the categorization the criteria for a given specific label. What are the features that cause a data point to receive that label? Generative model that want to predict the feature of a label, then use this feature to generate the new example of the data. It's something like first we have to regenerate the data, like they're going to learn it, and then they're going to reverse engineering, they'll do it. So generative model trained as generate image of a that animal can attempt to create an image of the fish based on the what it thinks make a fish different from the other animal. So image generation is a frequent use for the generative model. So if you see any of generative model, it will be image generation study. So now we'll talk about the types of the generative model. So many types are there actually, and then if you can see around the use of the multi-layer deep learning neural network structure, neural network is there. So first one is the auto-regressive model. Predict the next data point in a sequence based on the previous data instances. It's called transformer Excel at a NLP. Diffusion model create a new data by gradually adding the noise. It's a diffusion of the data, like it's something that adding into the one model, then we'll get the then figuring out how to remove the noise and yield over network. Then what we have the generative adversarial that the network, it's a pair of discriminative model together in comparison with the goal being they generate to create the output that fool the discriminator. Then what we have is the variable autoencoder compress the input data with an encoder, then reverse the process with the decoder to create the new sort like a new similar data. Flow-based model learn the relationship between the simple complex distribution of data through the reverse mathematical operation. Okay. So now we'll come to the probability model. It's actually going to use the probability distribution to represent the data and estimate the joint probability, to estimate the joint probability. Others, that model what we have, the classical, it's not going to use the joint one. Instead of they're going to use the conditional probability. That one question will come into the in that like that the next or in the that the last of the session. Then what we have the Bayesian network. Bayesian networks is actually graphical representation of the various possible relationship and given for the set variable classifiers that had no dependence on the features. It is conditional independent and they are used to model uncertainty by encoding the probability distribution relationship among the variable. Then HMM is there. HMM, hidden Markov model. It's a statistical model that so that the represent the transition between the state in a Markov process where the system state is partially observable through the set of the observation. It is going to predict on the data that are underlying process and hidden state. Each of the simple has a known outcome. Then what we have a neural like network based upon the model. In that first one, what we have is the generative adversarial network. In that, based on the machine learning and deep learning, two stochastic neural network, a generator and then discriminator. So that we're going to compete against the each other to provide the more accurate predictions and realistic information. Basically, a GN is an unsupervised machine learning technique that make it possible to automatically okay, so possible to automatically find and learn different pattern in the input data and then it's going to create an incredibly lifelike rendering of the various object people scenes and all. Then one more is there is called variational in that so that the auto encoder, it's a probabilistic model that learn encode decode the data and then they are going to learn to the latent representation, like we're going to create a simple a virtual feature space and then can generate so new sample from the learned latent space, like GNVI is also based upon the neural network encoder, which has combination of two neural network. It's a encoder and decoder here, generator and discriminator and all. Some other type flow-based model, complex from the simple flow, energy-based model also refine the scalar energy function that assign low energy to data point that resemble the training data and high energy to the analytical data points. It's a combination of high or scalar energy function and high energy. So now we'll come to the actual GAN model, how GAN model works and all. I think that one more that the session was going on, no? Oh, is it audible now? Yes, sir. Okay, sorry. I think that parallelly one more session was going on, no? Okay, I think that the like that the video I will upload it so that you can go through from the from the starting itself. Is it okay? Yeah, fine. So GN model that generate the new relational data by learning from the existing data is actually Ian Goodfellow, that book what we are following, Goodfellow. It was introduced in the 2014. It's actually they enable machine to create a content like image, video, and the music. It's something like, let's say we have a very low resolution image is there, so we can create the high resolution image. So it's a class of generative model, no expressive model, but allow one to sample, but the other to the distribution. Sampling is done using the neural network, and so what they will do, they're going to a like for a generative model, we have the discriminator, generator A. In that, we're going to like input the random noise, transform into the sample from the model distribution. Discriminator is going to a neural network that distinguish between the data came, it's a fake or the real. Okay. So how it's going to work it out? We have the random input, then it's going to like a generator. It came the like, so that the fake image, and we gave the original real image. Then we'll be having the discriminator. So then we're going to update it. If it is real, fine. It is fake. Again, we'll go to the here. Then again, try to superimpose the model, and we'll get the actual image. We'll get it out. So this is the how the GN is work. Random input is there. Real image will giving. Generator will be there. Let's say this came the fake image and this is a real image. Then we are going to give a discriminator. We'll get the either real or either fake. If it is fake, we're going to again feed it to the update like updation. Then we'll come to the back. So until unless we'll get the actual like a generative model and all. So that how it's going to work? It's a generate the create a fake data. Then after discriminate evaluate the data. Then after feedback loop. Okay. So, and there's also what is the difference between the generative AI and the traditional machine learning? Synthetic data. It's not the actual data we are going to generate, or we are going to create a new set of the data. Okay. And then here we'll be having the generator versus it's like a discriminator. And here will be the training with the adversarial. Like it's something the updated will be there. We have to update all the time. Then that so that the output will be the realistic. Let's say I gave image, will give the image only. But here predicted outcomes will be there. Supervised machine learning, minimize the error. Here training will be there. We have to train it until unless we got. Here we can do the classification or the regression. We are not going to say like regenerate the things like that one class or second class. Here in the traditional machine learning, we have to just to classify or regression. We have to do it. So image where we can use it out, image generation, super resolution, like improve the resolution of the image, or even with the data augmentation, like we have to generate more data, synthetic data, and we can get it out. Text to image also we can do auto. So create a new data similar to the real world data. Go beyond classification to generate the content used in the art, gaming, healthcare, and data science. So we'll come to the what is the architecture of the age GNN. No, it's not the GNN, it's a GN. It's a generative adversarial network. GN consists of two that work together. It's a one is the generator model, and second one what we have discriminator model. Discriminator model it will be something will be having a classify or identify fake or real. So generative model is a deep learn like in that the network. It's random noise as an input to generate the realistic data. Sample like image or text. It learned the underlying data pattern and then we'll be getting to the back propagation. So like we have to generate. It's a reverse engineering. Okay. So what we have to do, we have to minimize the loss. It's called reconstruction loss. So we can see around here it's logarithmic function, and it's going to fool in the discriminator JJ, and then GJ to generate sample for the random soil, like that's the noise, and DJ is actually it's going to discriminate the estimated probability that generate the sample is real or not. Then another model what we have is the discriminator. Discriminator is the actually classifier. It's going to distinguish real data from the generated sample. Through training, it refines the parameter to improve the detection of the fake data when working with the image. It uses the conventional layer to extract the feature and in that enhance the classification accuracy. Okay. So how it going to work it out? Latent that the random variable. It's like something we'll call the noise. It's going to generate the fake sample, real data, discriminator condition is correct, is fine. If not, we have to do the fine tuning. Okay. So this is the min, like it's the min, like the max loss function for the generator and like a discriminator. So generator tries to minimize the loss and discriminator tries to maximize it. So means detect the faculty. So we have to come up with the balance between the generator and all. So that how does that the GN work? GN trained by having two network. It's a generator. Then the we have the discriminator compete and improve together. Okay. So generator will be the first move. Generator start with random noise like a vector random number. It uses noise as a starting point to create a fake data sample such as generated image. Then it's going to internal layer transform this noise into the something look like real data. Then second terms will be the discriminator. The real discriminator receives the two types of the data. Real sample from the actual training data set, then fake sample created by the generator. So then discriminator job is to analyze the each input and find whether it's real data or something the generator cooked up or not. Its output probability score between the 0 to 1. If a score is going to be 1, data is likely to be real. Is 0, suggested to be the fake. It's a binary classification. So if someone want to work for that, so that the molecular classification, even the people can do it here also. So then adversarial learning. If the discriminator correct classify real and fake data, it get better at its job. If the generator fool the discriminator by creating the relative fake data, it receives the positive output and discriminator is penalized for making the wrong decision. So that's how the training will happen. Updation until the will get the look like of the real data. Then after generator improvement, each time the discriminator makes the data for the real, generator learn from the success. Through many iterations, the generator improve and create a more convincing fake sample. So this is how things we do the convincing sample. Then after discriminator adaptation, like it's something also learn continuously by updating itself, spot the fake data. Constant back and forth make both network stronger over the time. It's something, it's a continuous learning process. Okay. Then after, as the training continues, the generator becomes the highly proficient at the producing the relation data. Eventually, the discriminator struggle to distinguish the real from the fake so that GN has reached a well-training state. It's something starting there will be some sort of fake data they'll be able to classify or distinguish. But as the time progress, what they will do, it's like even that discriminator they are not able to classify or distinguish from the real to fake. So at this point, generator become highly produced synthetic data that can be used for the different applications. So that's how we have to generate the regenerated data, even that can be used for the biomedical applications and all. So this is the algorithm that how it will go. We have to start with the generator. then it will go to the real fake into the discriminator. If it is correct, it will learn again the both generator discriminator. If not, it will come back to the again to the data like a generator. It will go until it going to create a convincing real look like data set and all. So what are the types of the GN? It's called vanilla GN. It's a simple types of the GN. It consists of the generator. It's based upon the multi-layer perceptron. The model optimizes its mathematical foreign function using the stochastic gradient descent. Second one, conditional GN. It adds an additional conditional parameter to guide the generation process. Instead of generating data randomly, they allow the model to produce specific types of the output. I'll say I have to generate the image. It will be the image will be created by. I'll say that you have to generate the signal process it should be a signal. They'll create the like a signal. Then after deep convolutional DGCAN are the among the most popular type of the for the image recognition. DGCAN is deep convolutional network. It's a CNN extension will be there. Then what we have the that the Laplacian will be there is actually designed to generate ultra high quality images using a multi resolution approach. It's a Laplacian pyramid approach. Then super resolution image, like it's something that very old image, that image is there. We can create the very high resolution image and all. So where it can be used, where it can be used for that GM. Actually, it's primarily image generation. Okay. So can generate the realistic image avatar in high resolution while learning the pattern from the training data. Transform image between the while preserving the key feature. Example, converting day into the night, sketches to the realistic image, changing the artistic style. Create the visual from the textual description. It's the AI generated art or automated design. Generate the synthetic data to improve the machine learning model. Help in the making from the more robust and generalizable in the field with the limited delivery data. Upscale, raw, like it's going to be a low resolution image which helps in the improving the clarity for the application like medical imaging, satellite imagery, and then video enhancement and all. So now we'll come to the DGCAT. It said like again similar way, GN is there plus CNN or GN plus CNN. DGCANs uses CNN architecture as a stable architecture to train GN. It achieves the adaptable certain architecture constant to GN fluent by replace the pooling layer with the strategic convolution in the discriminator and transpose convolution generator. It's again similar way what we have used for the CNN, but it is replace the pooling layer with the strided convolution in discriminator and transpose convolution layer into the generator. Uses the batch normalization in both generator and discriminator. Remove the fully connected layer. Uses the ReLU activation in a generator for the all layer except the output which uses the tan H. We, in the output will not use the ReLU, will use the tan H and use the leaky ReLU activation in the discriminator for the all array. So this is the one paper actually. So you can go through that if you want to. So DGCAN like how conversion is there? 1, 2, 3, 4. Then we have the generator and all. So now we'll come to the one more variational autoencoder. It's actually a generative model. In going to use to the machine learning to generate the new data in form of the variation of the input data they are trained on. Let's say I have given the signal. They're going to also generate the signal only. Okay. So like all encoder, variational encoder are also going to use the deep learning model comport or the encoder that learn to isolate the important data variable. Encoder. There we have the generator discriminator. Here we have the encoder and decoder. So it's going to encode and learn the isolate important that latent variable. from the training data and decoder that uses the those latent variable to reconstruct the data. Like it's we have to uh, like at the bottleneck we have to compress it, then it's going to expand it. So whereas most autoencoder architects encode a discrete fixed representation of the that the latent variable. So VI encodes a continuous one. It means time series data. Okay, probabilistic representation of the latent space. This enable VN to not only accurately reconstruct the exact original input, but it can be used for the generate the new data sample resemble to the original input data. So actually, it is done by whom? It's a P. Kingna and Max Willing in that auto kind of like a Bayes. What is the latent space? Latent variable underlying variable of data inform the way data is going to distribute it. It's something encoder. It's a learning like how the data is distributed. So that will say latent space, but are often not directly distribution. So that we can see through the directly observable eye. For useful visualization, the concept of the latent variable, imagine a bridge with a sensor that measures the weight of the each passing vehicle. Naturally, there are different kinds of the vehicle that uses the bridges from small weight to the high convertible hues. But because there is no camera, so we have no way to detect if a specific vehicle is a convertible, sedan, or truck. However, we do know that types of the vehicle significantly influences the vehicle height. So it's how that latent space will see. So they are going to do latent space and dimensionality reduction. Auto encoder latent space through the dimensionality reduction. It means the compression of the data into the lower dimensional space. It's a like encoder is there. Then we have the bottleneck. Then decoder will be there. It's a compression will happen. Then it will go to the expansion. So what they will do, they're going to like even in the machine learning also mathematical dimension correspond not for the family special dimension for the physical, but for the feature of the data. For example, 28 by 28 pixel, black and white of a hand digit like a digit, we can be written as a 78 like a 784 dimensional vector in which each dimension correspond to the individual pixel. Their value will be range from the 0 to 1. Same image in color might be represented as a 2352 dimensional vector, in which 784 pixel represents in the 3 dimension, like it's a RGB value. It's a way of presentation. However, not all dimension contain useful information because that we told that every features can't be giving the useful information. So in that case, so actual digit itself represent only a small fraction of the image. So most of the input space is background noise. So compressing that down to the only dimension containing the relevant information that will be the latent space can improve the accuracy, efficiency, efficacy of the ML task and algorithm. So this is how the things will go. Encoder, input data is there. It's the compressing is happening. Here bottleneck, data got encoded. Now they have learned it. It's going to increase it until they're going to reconstruct the data. Encoder, latent space, and then decoder. So what is the architecture of that? What we have the encoder is there. Then we have the latent space is there. Then decoder will be there. So encoder, understanding the input. The encoder takes input the data like image or text, learns its key feature. Instead of outputting the one fixed value, it produces the two factor, mean, standard deviation. Latent space, adding the some sort of randomness. Instead of encoding input as a one fixed input, it pick a random point within a like range given by the mean and standard deviation. This randomness lets the model create slightly different version of the data, which is useful for the generating new and realistic sample. So then the third one what we have is the decoder, reconstructing or creating the new data. So that decoder takes a random sample from the latent space and try to reconstruct the original input. Since the encoder gives a range, decoder can produce the new data similar but not identical to what it has seen. So and why is the auto encoder? So they're using a KL divergence function. It's actually in the vector form. Its goal is to minimize the like difference between the supposed distributions and original distributions. It's called reconstruction loss. Reconstruction loss also we can say. So what is the actually auto encoder? Auto encoder is something like we'll be having a self-supervised system. They're going to training going to compress the data, input data through the dimension reduction, then accurately reconstruct the data like decode their original input by the using that compressed representation. So on a fundamental level, the function of autoencoder it is to effectively extract the data for the more salient information. It means we have to take the those who have the very like information rich, it's latent, variable, and they are going to discard the irrelevant noise. So that is the purpose of that. What they will do the auto encoder. So what is that auto encoder structure? Encoder is there, bottleneck, decoder. So what they will do while the encoder and decoder network of the many encoder are built from the standard multi-layer perceptron, auto encoder are not confined to the any specific type of the neural network. Let's see, like others GN and all that we'll be having some specifics like a CNN type will be there, some other model will be there. But for this, we don't have any specific like model will be there. Auto encoder used for the computer vision, conventional that the neural network and are thus called conventional encoder. Auto encoder built that architecture and that going to use for the multiple fields like computer vision and then music. A key that benefit of the auto encoder is that they're going to reduce the algorithm like the PCA is that an auto encoder can model non-linear. PCA is actually for the linear model. For that reason, so that the nodes of the autoencoder neural network typically uses the nonlinear activation function. In many autoencoder applications, the decoder serves only to aid in the optimization of the encoder, thus is discarded after the training. In various autoencoder, decoder is retrained and used to generate the new data point. So now we'll take talk about the what is the difference between the VAE and then GAN. VAN are often compared with the generative adversarial network, another model architecture used to generate sample resemble training data, especially for the images. Like VA, GA are for the joint architecture combined to the neural network, a generator like network, and then discriminator to like classify. The two network are trained adversely in a zero sum game. The feedback from the discriminator is used to improve the output, and generator under the discriminator is going to no longer able to discrete the fake sample. Okay. So now we'll solve some example. In this, in the generative adversarial network, what are the two neural network involved? Encoder or decoder? No, because it's going to be variational auto encoder. Feature student? Nothing. Classify and regression, it's going to be a traditional method. It's going to be a generator. It's like a generating the fake image or fake data and then discriminating between the real and the close one. When the Gaussian point is used for the MAP estimation, what type of regression is going to use? It's actually a ridge. This is going to be a lasso. So L2. So what is the input? What is the input to the generator network in the like GN? It's going to be a what? Like training data? No. Output for the distributor? No. It's going to feedback, not the input. Encoded representation, it's not the encoding. Not the encoding. It's a random noise vector for the generating. For the generator, it's a random noise vector. So, what is the bottleneck in a auto encoder? It's something they're going the so the layer where dimensionally reduction occurs. Okay. What is the key advantage of using the variational autoencoder over traditional autoencoder? VI is the computational like it's going less expensive. We can't say. VI provide more structure and meaningful latent representation. Yes. So actually, that VI can be VI can be expensive. VI automatically classifies the input data. No, they are going to reconstruct. It's like a encoding means learning and then compress it, then decode means reconstruction. VI requires less training data, we can't say. So it means VI provide the more structure and then meaningful letter representation. So what is the advantage might an ensemble classifier have over single classifier for a cardiac disease email? So ensemble methods are always faster comparatively. This is not always possible. They can capture the different aspect of the data, reduce the prediction variances. Yeah, because in simple learning, they will take one batch, second batch, third batch, and then we can give the for the particular. We'll take the analysis for the CT image and all. It's a this is diagnosis we can't take for the full X-ray. We have to take wherever it's going to break in out and all. So we'll take. So it means reduce the prediction variances. So it's this. So this is going to correct. They require the fewer feature to be extracted. No, if we take the full, it's going to more feature to be taken. They eliminate the need for the ground truth level. No, that we need for the ground truth level and all. So this can't be. So first one is the like second option. So then after, which why might processing the extract the region of interest to be beneficial in the cardiac MRI analysis compared to the using the full image? Let's say I told already previous one. If you take the full MRI is there. If you take for the full all image, what happened? It going to it will become more data set and all. It reduce the noise and help the student focus on the relevant application. It help to reduce the noise. Means let's say MRI. Let's say I have some discrepancy in the images here. If we take for the all, it become the redundant or noise. So we'll take whatever it's going to reduce the noises. It required for the all scenario. No, it's actually if we do for the all, it will so if for all image dataset, it's going to require for the all CNN application. So it can't be. It makes the data more colorful and visually appealing, but it will going to have the complex architecture or even computationally expensive. It reduces the number of class to predict. No, we have to classify either there is some disease is there or not. The class will be same always. Only thing that the input or the data point where we are going to figure it out, it's going to change. Like if we take the specific to the interest of region, it's going to give better results. It's going to reduce the noise and all. So, what function does a generative model learn from the descriptive model? A generative model, it's going to learn joint probability. joint probability. It's we have the generator, then discriminator, then it's going to combine with that. But if you see for that other traditional model, it's going to be a conditional probability. It's going to be this one. So for this GAN, it is correct. This is for Bayesian or traditional method. It's a data set distribution. That's correct only. BY classification, but it's not going to make sense in that. So what is the difference between the Bayesian regression and then map estimation? Map estimation is actually for the only point. Bayesian can go for the full. Bayesian regression provides the predictive distribution rather than the point estimate. Okay. What is the last one? What is the dice coefficient used for the medical image segmentation? Actually, this is going to find out the that the measure of the overlap between the predicted segmentation and the ground truth. Now, so that's all for today. So we can wind up the session. So to today's session, we have seen around that that the map point. So today we have discussed that the map estimation, then the Bayesian regression, and generative adversarial network and auto encoder. So now we are left with the one more week. In that we'll see a structure probability that the model, and then the it's going to be a like that the Monte Carlo methods and all. So hopefully, and then one more class will be there, extra classes that will be on Tuesday. So we'll take some examples from the course and then we'll explain full, almost all the model and all. So that will going to be a not like it's not going to be in this week, but it will going to like definitely in the that the next week. Any doubt is there in this?
Thank you.
Okay, thank you.